In this video, we will prove this equation of chemical potential by adding an infinitesimal amount of helium into a room temperature gas mixture of helium and argon under constant enthalpy and pressure condition. Under constant HP conditions, mu is -T times delta S over delta N. We're going to use this equation to calculate the entropy change of an ideal gas that undergoes pressure change. The entropy of the added helium relative to its standard state is this. Dn is the number of moles of the added helium, and then over here this is simply the partial pressure of the added helium divided by P naught. The absolute value of the entropy of the added helium is thus this relative amount plus the entropy in the standard state. There are two terms. What about the change of the entropy of the pre-existing helium gas? Again, we'll use this equation. We'll use its final pressure over its initial pressure multiplied by -nr. So we get expression here for the pre-existing helium. Similarly, we get the entropy change for the pre-existing argon. Okay, again, we add this three components together. We get the overall change of the entropy of the entire system. The first two terms are the entropy of the added helium. This term is the entropy change of the pre-existing helium. This is the entropy change of argon. It looks very complicated, and over here we have actually 1, 2, 3, 4 terms. But again, we can just use this approximation to simplify all these terms. For every single term that has logarithm, we'll just use this Taylor expansion of logarithm. As long as delta is very close to 0, the natural logarithm of 1 plus delta is approximately delta. So we can simplify this logarithm and also this logarithm and then this logarithm, and we get the final expression for the exact differential of the entropy of the entire system. It's here. We have only two terms. So again, under constant HP condition, we get the chemical potential of helium by doing -T times ds over dn. ds comes from here, only two terms. We just plug in those expressions, and then finally we get this expression for the chemical potential of the helium gas. It's RT times the natural logarithm of the partial pressure of helium over P naught minus T times the standard molar entropy of helium. So again, we get this equation, but this looks a little different from the equation we commonly use over here. So what's the difference? You can see this term RT times the natural logarithm of the partial pressure of helium over P naught is exactly the same as this one. So is this equal to the standard chemical potential of helium? The answer is yes. If we assume the standard molar Gibbs energy is the same as the standard Gibbs energy of formation, then the standard molar entropy is H minus G over T. That's simply just 0 for this helium at room temperature, and this part disappears. And also we know the standard chemical potential of helium is 0. If we make this assumption, that means this equation and this equation are essentially the same. We derived this same equation of chemical potential under the constant temperature pressure condition, constant TV condition, and in this video, constant HP condition. Again, the standard chemical potential of helium is 0 if we make this assumption. We can also assume the standard molar Gibbs energy is the standard enthalpy of formation minus temperature times the standard molar entropy. I mean, we can do this as well. This time, this standard molar entropy is only 0 at 0K for a pure crystal. So this is supposed to be positive for the helium gas. But nonetheless, we will end up with the same expression for the chemical potential. So we get this equation, and this part is simply just mu not helium. Why? The standard chemical potential of helium is again the standard molar Gibbs energy of helium, which is delta H minus T delta S T times the molar entropy. And we get this equation because the enthalpy of formation of helium is 0 when it's in the standard state at room temperature. So in this section 5.9 chemical potential, we have proven actually numerically and analytically this equation, and whether the condition is constant Tp, constant Tv, or constant Hp. The chemical potential may take various forms, but its essence never changes.